Welcome to Grandpa's Late Nights. It's good to have you here. Wherever you are right now, whatever corner of the world you've curled up in tonight, come on in and get comfortable. Pull the blanket up a little higher if you need to. Let your shoulders drop away from your ears. There's a lamp somewhere in the house I've left burning low, and the porch light's on. And there's nothing at all you have to do for the next little while except lie there and let an old man talk you gently towards sleep. Before we begin, let me ask you something, the way I always do. Where in the world are you listening from tonight? What time is it in your corner of the night? I like to imagine you out there, some of you in a bed with the rain coming down. Some of you on a couch with a cold cup of tea gone forgotten on the table. Some of you on a long train ride watching the dark slide by. I can't see you, of course. But I think about you. And if you've got a moment before your eyes get heavy, a quiet like or a subscribe does more than you'd think to keep this sleepy little channel going. I'm a small creator, just an old voice in the dark, and folks like you are the whole reason the porch light stays on. To those of you who've already subscribed, thank you, truly, you keep an old man company. Now, I'll make you the same promise I always make. I'm going to try as best I can not to make tonight's story so interesting that it keeps you awake. But if it does, well, at least you'll have learnt something. I'd call that a fair trade. And here's the other promise, the important one. You don't have to follow every word. You don't have to understand all of it, or any of it really. That's not what tonight is for. If you drift off in the middle, that's not a failure. That's the whole idea. The ideas will still be here when you wake. The universe isn't going anywhere. So there's no need to concentrate, no need to keep score, no need to grip the thread too tightly. Just let it wash over you, slow and warm, like a tide coming in. We'll take it easy tonight. One small mystery at a time. No rush at all. So, let me tell you something strange. Something that, if you let it, might make you feel very, very small. And I mean that in the kindest possible way. Because sometimes feeling small is a comfort. Sometimes it's the softest feeling there is. Right now, wherever you are, everything you have ever seen, every star you've ever wished on, every galaxy in every photograph any telescope has ever taken. The whole sweep of the cosmos, as far as the most powerful instruments can reach. All of it. Every last speck of it might fit inside a single bubble. One bubble. And that bubble might be just one among an endless, uncountable number of others. Let that settle for a moment. I'll wait. There's no hurry. The part of the universe we can actually see, what astronomers call the observable universe, is enormous beyond any words I have for it. It stretches about 93 billion light-years across. Now, a light-year is already a number that breaks the mind a little. It's the distance light travels in a year, and light is the fastest thing there is, crossing the gap from the sun to your face in about 8 minutes. Travel at that speed for a full year, and you've gone 1 light-year. Now do that 93 billion times over, and you've measured just the part of the cosmos we can see. Every galaxy, every nebula, every pinprick of light in the night sky, all of it tucked inside that 93 billion light-year sphere. And tonight I'm going to tell you that our best theory of how it all began suggests, quietly, almost reluctantly, that this entire, staggering, incomprehensible thing might be nothing more than the inside of one bubble. A single pocket, and beyond it, more bubbles, not a few more, not a million more, possibly an infinite number more. Here's the image I want to leave with you before we slow down and take it all apart gently. Picture our whole observable universe, everything shrunk down until, compared to the larger structure it floats in, it's smaller than a single atom is compared to the entire observable universe. Smaller than that, actually, and even saying it that way doesn't do it justice. Because the larger structure isn't just big, it may be infinite. It may still be growing, right now, faster than you can imagine, spawning new bubbles endlessly off into a future with no end. That's the terrifying truth we're going to wander through tonight. Though I'll be honest with you, kiddo, I don't think terrifying is quite the right word. I think it's more like standing at the edge of the sea at night, when you can't see the far shore and you can't see the bottom, and something in your chest goes very quiet and very wide all at once. It's not fear exactly, it's awe wearing fear's coat. And by the time we're done, I hope you'll feel less afraid of it, not more. So here's what I'm going to do for you over these slow hours. I'm going to tell you what this theory actually is. The real physics, from the real people who worked it out, with the real names and the real dates, not some hand-wavy fairy tale. I'm going to tell you why it says there might be countless other universes, and I want you to understand that this wasn't something anybody wanted. The men who built this theory tried to get rid of the other universes. They couldn't. The math wouldn't let them. I'll show you why. I'll tell you what one of these other universes might be like, and it's stranger than you'd guess. I'll tell you why we can almost certainly never reach one, never even see one, no matter how long we look or how far we travel. And at the very end, I'll tell you about a real argument, a genuine fight, still going on, between brilliant people, some of whom helped invent this whole idea in the first place, about whether a theory that predicts infinite universes we can never observe is even science at all. But all of that is for later. For now, let's start where every good story starts. At the beginning. The very beginning. Let's talk about the Big Bang, and then let's talk about the strange little wrinkle in the first sliver of a second that changes everything. You've heard of the Big Bang, I'm sure. Most everyone has. The idea that the universe started out unimaginably hot and dense, and has been expanding and cooling ever since, for something like 14 billion years. That's the broad picture, and it's a good one, and it's true as far as it goes. But there was a problem with it. Several problems, actually, and to fix them, back in 1980, a young physicist named Alan Guth came up with an idea so bold it almost sounds like cheating. His idea was called cosmic inflation, and the heart of it is this. In the very, very first instant after the beginning, and I mean the first instant, a slice of time so short it makes a blink look like an eternity, space itself didn't just expand, it exploded outward at a rate that beggars belief. Not the stuff in space. Space itself. It stretched. Let me give you the numbers, slow and easy, and don't worry about holding them all. We're talking about the period between roughly 10 to the minus 36 seconds and 10 to the minus 32 seconds after the beginning. Now 10 to the minus 36 of a second. How do you even picture that? You can't, not really. It's a decimal point, followed by 35 zeros, and then a 1, all before you get to the first meaningful digit. It is a portion of a single second so small that if you tried to divide 1 second into that many pieces, you'd run out of universe before you ran out of pieces. It happened, began, and ended, all within the first flicker of the first tick of the first clock that ever was. And in that impossibly brief window, space doubled in size. And then doubled again. and again, over and over, perhaps 60 times, perhaps more. Physicists have a lovely, homely word for these doublings. They call them e-folds. 60-some e-folds, one after another, each one doubling the size of everything, all in less time than it takes light to cross the width of a single atom. Here's the way I like to think about it. Lying in bed. Take a single grain of something impossibly tiny, smaller than a grain of sand, smaller than a speck of dust. Smaller, in fact, than a proton, which is one of the little pieces that make up the heart of every atom in your body. A proton is already so small that you could line up trillions of them across the width of a human hair. Now take a region of space far smaller even than that, and in the tiniest fraction of a heartbeat, stretch it, blow it up like the gentlest, fastest balloon that ever was, until that speck smaller than a proton is suddenly big enough to see. Big enough to hold. Big enough, eventually, to become everything. That's inflation. A patch of space smaller than the smallest thing, ballooned up to enormous size in almost no time at all, and then, just as suddenly, stopping and handing the universe back over to the ordinary, gentle expansion we still see today, the slow drifting apart of the galaxies that's been going on ever since. Now, you might be lying there thinking, and it's a fair thought, why on earth would anyone believe such a wild thing? Space blowing up faster than light in the first sliver of a second from something smaller than a proton. It sounds made up. It sounds like the kind of story you'd tell to explain anything at all. And if that's where your mind went, good, that's exactly the right question to ask. Hold on to it, because the answer is the whole reason this theory is taken seriously, and we'll get there in just a little while. But first, let me tell you why Alan Guth reached for such a strange idea in the first place. Because he wasn't being fanciful. He was trying to fix things. Real, specific, nagging problems with the older, simpler Big Bang picture. Problems that kept physicists up at night, the way a small sound in the house keeps you listening in the dark. There were 3 of them, and inflation, remarkably, solved all 3 at once. That's the sign of a good idea in physics, by the way. Not that it explains one thing you asked it to, but that it quietly explains 3 things you weren't even asking about. Let me walk you through them, one at a time. Slowly, there's no rush. The first was called the horizon problem. And it's a beautiful puzzle, really. When astronomers look out at the universe in every direction, they see a faint, ancient glow left over from the early cosmos, a kind of afterglow of the Big Bang, filling all of space. And the strange thing about this glow is how astonishingly even it is. Look one way, and it has a certain temperature. Look the exact opposite way, billions of light years across the sky, and it has almost precisely the same temperature. The same to a remarkable degree of accuracy. Now, why is that a problem? Well, think about it this way. Imagine you filled a bathtub, part of it with hot water and part with cold. Left alone, the water evens out, doesn't it? The hot mixes with the cold until the whole tub is one comfortable temperature, but for that to happen, the hot part and the cold part have to touch. They have to mix. Heat has to flow from one to the other. Here's the trouble. Those 2 opposite patches of sky, the ones with the same temperature, are so far apart that, in the ordinary Big Bang story, they never touched. Not ever. There wasn't enough time in the whole history of the universe for light or heat or any signal at all to travel from one to the other. Nothing moves faster than light, remember, so how did they agree on a temperature? How did 2 regions that never met, never exchanged so much as a whisper, end up so perfectly matched? It's as if you walked into two houses on opposite sides of the world and found the thermostats set to precisely the same number down to the last decimal, and then learned the two families had never met, never spoken, never even known the other existed. You'd want an explanation. You'd need one. Inflation gives you one, and it's elegant. It says, those two patches did touch, long ago, when everything was unimaginably tiny and cozy and close together. They mixed. They came to the same temperature, snug against each other like two people sharing a small blanket. And then inflation happened, and space blew up, and those two patches, already agreed, already matched, got flung to opposite ends of the sky. They're far apart now. But they weren't always. They were neighbours once, before the great stretching carried them away from each other. That's why they match. They remember being close. Isn't that a lovely thought to fall asleep to? That the farthest apart places in the sky were once side by side, and still carry the memory of that closeness, written in their temperature billions of years later. The second problem was called the flatness problem, and this one's about the very shape of space itself. Space, it turns out, can be curved. This is one of those ideas that sounds like nonsense until you sit with it. We usually think of space as just nothing, emptiness, but according to Einstein's work, space has a geometry, a shape, and that shape can bend. It could curve back on itself, like the surface of a great ball, so that if you travelled far enough in a straight line, you'd eventually come back to where you started. Or it could curve the other way, spreading open like a saddle, endless and flaring. Or, and this is the strange case, it could be perfectly flat, balanced exactly on the knife's edge between the two. And when we measure our universe, it looks flat, astonishingly precisely flat. Now here's why that's a puzzle. Being flat, in this cosmic sense, is a bit like balancing a pencil on its point. It's possible, but it's a delicate, precarious kind of possible. The tiniest nudge in the early universe, the smallest deviation from perfect flatness, would have grown and grown over billions of years, until by now space would be wildly, obviously, curved, one way or the other. For the universe to look flat today, it would have had to start out flat to an almost absurd degree of precision, like finding that pencil still balanced on its point after 14 billion years. You wouldn't say how lucky, you'd say someone must be holding it. Inflation is what holds it. When you take any surface, no matter how curved, how wrinkled, and you stretch it enormously, blow it up to a colossal size, it flattens out. Think of standing on the surface of the Earth. The Earth is a ball, curved all the way around, and yet the ground beneath your feet looks perfectly flat, because you're so small compared to how big the whole thing is. The curve is still there, it's just been stretched far beyond anything you can perceive. Inflation does that to the whole universe. Whatever shape space had at the start, inflation stretched it so violently that any curve got ironed out, flattened, smoothed, until the little patch we live in looks flat as a still pond. Not because it was set up that way, but because the stretching made it so. The problem dissolves. And the third problem, the last of the trio, was called the monopole problem. This one's a touch more technical, but the shape of it is simple, so let me give it to you gently. Some of the deepest theories physicists were working on in those years, grand attempts to unify the forces of nature, predicted that the early universe should have produced certain very heavy, very peculiar particles. Magnetic monopolies, they were called. Think of an ordinary magnet. It always has two ends, doesn't it? A north pole and a south pole. Cut it in half, and you don't get a lonely north and a lonely south. You get two smaller magnets, each with its own north and south. Try as you might, you can never seem to get just one pole all by itself. A monopole would be exactly that impossible thing, a single magnetic pole, alone, north without south, or south without north. The theories said the early universe should have made a great many of them. Heavy ones, they should be scattered all through the cosmos. And yet, we've never found a single one. Not one. The sky is empty of them. Inflation solves this the way a very small drop of ink solves the problem of a too dark glass of water. Suppose the early universe did make those monopolies. Then inflation came along and blew space up so enormously, so violently, that whatever monopolies existed got spread out across a volume so vast that there might be, at most, one or two of them in our entire observable universe. Diluted to nearly nothing, thinned across the immensity until you could search your whole life and never stumble across one. Not because they were never made, but because inflation scattered them so thin. The problem doesn't need them destroyed, it just needs them spread out. And spreading things out is the one thing inflation does better than anything else in all of physics. 3 problems: the horizon problem, the flatness problem, the monopole problem. 3 separate headaches that had troubled cosmologists for years. And one idea, a fraction of a second of runaway stretching in the newborn universe, quietly answered all 3 at the same time. That's why people sat up and paid attention when Alan Guth published his idea in 1980. Not because it was flashy. Because it was thrifty. 1 stroke, 3 problems gone. But, and here we come back to that good skeptical question you were asking a little while ago, solving old problems isn't quite enough. Any clever person can dream up a story that explains things we already know. That's the easy part. The hard part, the part that separates real science from a nice tale told in the dark, is this. Does the idea predict something new? Something we didn't know to look for? Something we can go out and check? Because if a theory only ever explains what we've already seen, you can't really trust it. It might just be a story that happens to fit. But if a theory sticks its neck out, if it says, go look over there, and you'll find this specific thing you've never seen before, and then you go look, and it's there, just as promised. Well, now you've got something. Now you've got a reason to believe. And this, kiddo, is the part I most want you to hear before you drift off, because it's the reason we take all the wild stuff seriously at all. Inflation didn't just tidy up old problems, it made real predictions. Specific ones. Testable ones. And they came true. Here's the first and most beautiful of them. Inflation says that when space blew up in that first instant, it should have left behind a very particular pattern, a faint set of ripples, tiny variations seeded into that ancient afterglow I mentioned earlier. And not just any ripples. Inflation predicts that these ripples should be spread across all different sizes in a very specific way, almost, but not quite. Perfectly even across every scale, nearly the same at large sizes and small sizes, but with a slight, deliberate tilt. A gentle lean toward one end. Physicists gave this lean a name. They call it the spectral tilt. Now here's the thing that gives me chills, in the good way. Physicists calculated, from the theory, roughly how much of a tilt there should be. And then they went and measured it. There's a spacecraft called the Planck satellite. It spent years, from 2013 through 2018, staring at that ancient afterglow with extraordinary precision, mapping those faint ripples across the entire sky. And when the measurements came back, they found the tilt. It's captured in a single number that physicists write as n sub s, and its value came out to about 0.965. Just a hair less than 1, just the small particular deviation from perfect evenness that simple inflation had predicted decades before. Not 1, not exactly even, but measurably, precisely, a little less than 1, exactly the kind of gentle lean the theory called for. Think about what that means. Someone did a calculation about the first 10 to the minus 36 of a second of all existence, based on this wild idea of space exploding outward from a speck. And then, years later, a machine floating in the cold dark measured the sky and found the answer matched. That's not a story that happens to fit. That's a prediction that came true. And there's more. Remember the flatness problem? How inflation should have ironed space out perfectly flat? Well, that's a prediction too. Inflation says the universe should be flat. Very, very flat. And when we measure the actual geometry of space using that same ancient light, we find it flat, confirmed to within about 0.4%. Which is to say, as flat as we can possibly measure, exactly as the theory demanded. This is why, when you hear a physicist call cosmic inflation our best theory of the early universe, they're not just being poetic, and they're not just fond of it. They mean it earns the title. It solved 3 old problems in one stroke, and then it stuck its neck out and made predictions about things nobody had measured yet, the tilt of the ripples, the flatness of space. And when we finally went and looked, the universe agreed. 0.965, flat to within 0.4%. The numbers came back on the theory's side. So keep that firmly in mind as we go deeper into the night, because it matters enormously for everything that follows. Everything I'm about to tell you, the other universes, the infinite bubbles, the copies of you, all of it, grows out of this same theory. The theory that got the tilt right. The theory that got the flatness right. This isn't idle speculation dreamed up by someone who wanted the universe to be exciting. It's the strange, uninvited shadow cast by our single best, most carefully tested picture of how everything began. And that's what makes it so hard to shake. If inflation were just a nice story, we could set the multiverse aside and sleep easy. But inflation isn't just a nice story. It's a story the sky itself has confirmed, in number after number. And that same confirmed story, when you follow its own equations honestly, all the way to the end, the way its own inventors did, sometimes to their dismay, seems to hand you infinity whether you asked for it or not. But I'm getting ahead of myself. That's a thread for a little later, when we talk about the engine that drives all this stretching, a strange kind of nothing that pushes instead of pulls, a field with a name and a quiet quantum trembling inside it that turns out to be the seed of every galaxy in the sky, and, if you follow it far enough, the seed of endless worlds. For now, though, just rest with what we've built so far. A tiny patch of space, smaller than a proton, blown up to enormous size in the first flicker of the first instant. 60 doublings, one after another, 3 old riddles solved in a single stroke, the matched temperatures across the sky, the impossible flatness, the missing monopolies, and a theory that didn't stop at explaining, but reached out and predicted, and was proven right by a satellite reading the oldest light there is. There's something steadying in that, I think. In the idea that the universe, for all its strangeness, is at least a little bit knowable. That people sitting quietly with pencils and equations, and then patient machines floating in the dark, can actually work out the shape of the first instant of time and check their answer and find they were right. It's a comfort in its way. The cosmos is wild beyond words, but it isn't lawless. It keeps its promises. The numbers add up. So let your breathing go slow and even now. There's nothing you need to remember. If the words are starting to blur and drift, let them. We've laid the foundation tonight, and the rest of the story will keep. The tilt is still 0.965. Space is still flat. The little patch that became everything is still, somewhere far back, at the beginning of all things, doing what it did. And in a little while, when you're ready, we'll lean in closer and ask the harder question. The one that troubled even the people who dreamed this theory up. Not how the universe began stretching, but why, once it started, it might never have fully stopped. Rest easy for now. Stay with me, soft and slow, and let's keep drifting on into the dark together. So, the engine. If inflation is a car, then the inflaton field is the fuel, and it's very strange fuel. Not petrol, not electricity, not anything you could hold in a jar. It's a field, which in physics just means a number that lives at every point in space. A temperature field, for instance, tells you how warm it is at every location in a room. An inflaton field tells you something about the energy state of space itself, and in the very earliest moments after the beginning. That field was sitting somewhere it wasn't supposed to be. Let me try to picture it with you slowly. Imagine a ball, a marble, say, placed in a bowl. Left alone, it rolls to the bottom and rests. The bottom of the bowl is the lowest energy state available to it. That's where it wants to be. That's stability. Now imagine the marble is placed not at the bottom of that bowl, but on a wide, gently sloping plateau just to the side of it. It's not at the bottom, it's higher than it needs to be. And sooner or later it's going to roll down, but for now, just for a while, it's sitting up there, carrying energy it hasn't yet given up. That high plateau is what physicists call a false vacuum. The inflaton field, in the very first instant, was sitting on something like that plateau. It wasn't at its lowest possible energy state. It was stuck at a higher one, temporarily, not because anything was holding it there by force, but because the slope was so gentle that rolling down took time. In the jargon, this is called slow-roll inflation. The field rolls, but slowly, like a marble on a wide, flat surface with just the faintest incline. And here is the part that changes everything. In Einstein's theory of general relativity, energy causes gravity. We know that. Mass curves space, and so does energy. But there's a subtlety, a genuinely extraordinary subtlety, that took decades to fully appreciate. The way a field's energy curves space depends not only on how much energy it has, but on its pressure. And the false vacuum, that high plateau the inflaton is sitting on, has a very unusual kind of pressure. It has negative pressure. Pause on that for a moment if you can. Negative pressure. We're used to positive pressure. Air pushing out against the walls of a balloon. Water pushing down at the bottom of a tank. Positive pressure, in ordinary experience, pushes outward. But negative pressure is its mirror image. It's something like tension, a pulling inward, the way a stretched rubber band wants to contract. And in Einstein's equations, that distinction matters enormously. Normal positive pressure adds to gravity's pull. Negative pressure, it turns out, produces the opposite. It gravitates repulsively. It pushes space apart rather than drawing it together. The false vacuum, in other words, is a kind of anti-gravity machine built right into the structure of space itself, and once that machine is on, the expansion it drives isn't slow and gentle, it's exponential. Each moment, the space already there doubles, and then doubles again and again. Not moving through space, the way a rocket moves, but space itself stretching. Every point pulled from every other point with a force that grows the faster it grows. There's no speed limit to the expansion of space itself, and inflation exploited that with something close to abandon. 60 doublings or more in a window of time so small it makes a nanosecond look like an age. A region far tinier than a proton, inflated to a scale large enough to become everything you have ever seen. Then the marble reached the bottom of the bowl. The inflaton field rolled off its plateau and settled into its true lowest energy state, the actual minimum, the true vacuum. And when it did, all that energy it had been carrying, all that coiled potential, was released in a burst. It didn't vanish. It converted into a hot, dense, screaming plasma of particles, quarks, electrons, photons, the basic ingredients of everything. Physicists call this moment reheating, because, in a sense, it was. The exponential expansion had cooled things down to nearly nothing, but the energy of the inflaton field, released all at once, heated the universe back up to almost inconceivable temperatures. And that moment of reheating is what we usually call the Big Bang itself, the fireball that physics has traced so carefully, the hot plasma that eventually cooled into atoms and stars, and the faint microwave glow we still detect today. Inflation set the stage. Reheating lit the lights. And then, the conventional story of cosmology begins. But there's a thread here I want to pull on, gently, before we move on. Because the inflaton field and its negative pressure and its repulsive gravity aren't entirely new concepts in physics. There's an older ghost here, a very famous one. In 1917, Albert Einstein was trying to apply his newly finished theory of general relativity to the universe as a whole, and he ran into a problem. His equations, as written, predicted a universe that was either expanding or contracting. It wouldn't sit still. But Einstein, like everyone else at the time, believed the universe was static, not moving. Just there, eternal and unchanging. So he did something that physicists don't like to do, but sometimes do anyway. He added a term to his equations, a fudge factor, a number he called the cosmological constant, usually written with the Greek letter lambda, whose whole purpose was to provide a gentle repulsive push against gravity's tendency to pull everything together and hold the universe in balance. It was, by his own standards, an uncomfortable solution. Inelegant, something stuck in to make the math behave. And then Edwin Hubble found that the galaxies are receding, that the universe is in fact expanding, that the static universe Einstein had assumed was simply wrong. And Einstein, famously, called the cosmological constant his greatest blunder. He pulled it out of the equations and moved on. But here's the thing about great blunders. Sometimes they come back. In 1998, two independent teams of astronomers, one led by Saul Perlmutter, the other by Brian Schmidt and Adam Ries, were studying distant supernovae. These are exploding stars, and a certain type of supernova is remarkably consistent in its brightness, which makes them useful as cosmic measuring sticks. You can use them to figure out how far away a galaxy is, and then compare that to how fast the galaxy is moving away from us. The teams were expecting to measure the universe's expansion rate, and, more specifically, they expected to see it slowing down. Gravity, after all, should be pulling everything back, even as it expands, like a ball thrown upward, eventually slowing. What they found instead was that the expansion is speeding up. The universe is not decelerating, it's accelerating. Some energy embedded in the vacuum of space itself, some field we don't fully understand, is pushing space apart right now, today, all around you, all around everything. That something is what we now call dark energy, and it constitutes roughly 68% of the entire energy content of the universe. And when physicists looked at the equations and tried to model what dark energy might be, they found themselves reaching for Einstein's cosmological constant, the same repulsive term he had called his greatest blunder. It is, in a quiet, extraordinary way, the same physics. Not identical, inflation's repulsion was enormously stronger and burned out in a fraction of a second. Dark energy's push is mild by comparison, and it appears to be permanent. But they share a family resemblance. Both involve energy in the vacuum, producing a repulsive pressure that drives space to expand. The universe began with an extreme, brief episode of repulsive expansion, and it seems it's ending, in slow motion over billions of years, with a mild, permanent one. Inflation in the past, dark energy in the future, and you, lying somewhere between them, in the brief middle chapter where stars and planets and people exist. There's something humbling about that, and also something oddly beautiful. Now, let's stay with the inflaton just a little longer. Because before we get to the strange thing the inflaton did, the thing its inventors really didn't want, we have to appreciate something else it gave us, something closer and more personal. You and the chair you're sitting in, or the bed you're lying in, or the blanket you pulled up a few minutes ago. All of it. Stars, galaxies, planets, people, everything with a shape and a location in the cosmos. Here's how it happened. During inflation, while the inflaton field was rolling slowly down its plateau, while space was doubling and doubling, the field wasn't perfectly smooth. It couldn't be. At the quantum scale, nothing is ever perfectly smooth. There are always fluctuations, tiny, random, utterly unavoidable jitters in the value of the field, like the surface of a very still lake that still carries microscopic ripples even on the calmest day. These fluctuations are inherent to quantum mechanics. They don't go away. You can't engineer them out of existence. They are, in some deep sense, built into the fabric of reality at the smallest scales. Under normal circumstances, quantum fluctuations are unimaginably small. They live at scales far below what any instrument can measure. You would never notice them. They have no effect on the world of chairs and blankets and sleeping people. But inflation changed that. Because, as space expanded, doubling, enormously fast, it stretched everything within it, including those tiny quantum ripples. The jitters that had been living at scales far below an atom were stretched outward, first to the size of an atom, then a grain of dust, then a mountain, then a planet, then a galaxy cluster. Stretched to cosmic size, they became real, physical density variations. Tiny patches where the matter and energy were very slightly more concentrated, and other patches where they were very slightly less. Differences of perhaps 1 part in 100,000. That's small. But gravity is patient. Over hundreds of millions of years, those slight overdensities grew. Matter fell into them, slowly, the way water pools in the lowest points of an uneven ground. Gas gathered, compressed, ignited. The first stars were born inside those original fluctuations. And those stars gathered into clouds of billions, and those clouds became galaxies. And the galaxies clustered along the great cosmic web of filaments and voids that you'd see if you could somehow zoom out to the largest scale of all, the Milky Way. Andromeda, the local group. Every structure with a name, every place we've ever pointed a telescope. All of it grew from seeds, and the seeds were quantum jitters, stretched to cosmic size by inflation, which means something rather extraordinary when you sit with it. The quantum world and the cosmic world are not separate. The randomness at the Planck scale is the reason the large-scale structure of the universe looks the way it does. The Planck satellite didn't just confirm inflation, it confirmed that the universe's largest features have quantum origins. The spectral tilt in the CMB, the nearly but not exactly scale invariant pattern of fluctuations, is a direct fingerprint of those stretched quantum jitters. You are, in this very literal sense, a cosmic consequence of a quantum accident. The atoms in your body are made of elements forged in stars, and those stars formed in overdensities seeded by quantum fluctuations during the first trillionth of a second. The random jitter in the inflaton field, inflated to enormity, is why there is something here to see rather than a perfectly smooth, perfectly uniform void where structure never coalesced and nothing ever burned. It's a lot to carry into sleep, and you don't have to carry it consciously. Let it settle somewhere below thought, soft and slow. But here's a question worth parking before we go further. And you don't have to answer it now. Just notice it. If the quantum fluctuations were happening everywhere, if the inflaton field was jittering randomly at every point in space, and inflation was stretching all of those jitters outward, then why did inflation stop? Quick reminder, after years of lying awake with a racing mind, deep sleep finally became possible. Now learning comes easier, energy is real, and the mind stays sharp. Sleeping like a baby changed everything. If you want the exact system that made this possible, check the link in the pinned comments. And that question, why did inflation stop and what happens in the places where it didn't, is exactly where things get strange. Really, genuinely strange. Strange in a way that troubled the physicists who discovered it. Strange in a way that they tried for a while to make go away. It didn't go away. So let's drift into it, softly. The inflaton field, as we said, was rolling down its potential. Slowly. Gently. The marble making its way from the plateau to the bottom of the bowl. And in most of the space it was doing that. Rolling down, ending inflation, triggering reheating, giving birth to a hot universe. That's the story so far. But quantum fluctuations were happening the whole time. Not just the small structural ones that seeded galaxies. Every quantum field fluctuates, always, everywhere. The inflaton was no different. While it was rolling down the slope, random quantum kicks were nudging it in every direction, including upward, back toward the high plateau, back toward where it started. Most of the time, in most places, those upward kicks were too small to matter. The rolling down tendency dominated and inflation ended on schedule. But not always, and not everywhere. Here is the crucial thing, the crucial, uncomfortable, marvelous thing. In some regions, small ones, scattered randomly, the quantum kick upward was strong enough to push the inflaton back up the slope. In those regions, inflation didn't end. It kept going. The field was still up on its plateau, still producing negative pressure, still driving exponential expansion. While the surrounding space had quieted into a hot fireball, these little patches were still doubling and doubling and doubling. Now, here is where you need to think about volumes. When a region is inflating, it is growing. Fast, exponentially, each doubling makes it twice as large in every direction, which means 8 times the volume. So a region where inflation continues isn't just continuing, it's getting vastly, rapidly, almost incomprehensibly bigger. While the regions where inflation has ended are finite and fixed. The regions where it's still going are swelling at an exponential rate. And within those swelling, still inflating regions, quantum kicks are still happening. Most of the inflaton field within those regions is rolling down, ending inflation there too. But a fraction, a small fraction, is getting kicked upward again, keeping that subregion inflating. And that subregion is swelling. Do you see what's happening? The volume of space that is still inflating grows faster than inflation ends within it. Not locally, inflation ends in plenty of places. But the total volume of inflating space keeps increasing, because the rate of expansion outpaces the rate at which individual patches drop out. The inflating sea keeps growing, even as bubbles keep falling out of it. Inflation never stops. Not everywhere. Not overall. There will always be more inflating space than there was before. Regions end their inflation and quiet down into hot fireballs, one by one and here and there, scattered across the inflating hole. But the hole keeps expanding. The froth keeps bubbling, and it does so, as far as the equations are concerned, forever. This is what physicists call eternal inflation. The word eternal here means something specific. It means future eternal. Inflating space will keep producing new pockets of quiet universe forever into the future, without end, because the mechanism that creates them is also the mechanism that perpetuates the space they're being created in. There will never be a last pocket. There will never be a moment when inflation has finally, everywhere, finished. The man who first described this in its full form was Andrei Linde. Linde had already helped save inflation once. He'd been one of the architects of the slow-roll version, the new inflation of 1982 that fixed Guth's original graceful exit problem. And in 1986, pushing further into the mathematics of his own model, he described what he called a self-reproducing, chaotic inflationary universe. The idea was stark and strange, a universe that, once inflating, produces more inflating universe faster than inflation can end. Like a fire that throws off sparks, and each spark starts a new fire, and each new fire throws off more sparks, without limit, across an infinite and ever-growing dark. Alexander Vilenkin had glimpsed the essential idea earlier still. As far back as 1983, he'd worked out the basic framework of what we'd now call eternal inflation. The runaway self-creation that falls out of taking quantum fluctuations seriously inside an inflating universe. What both of them found, and this is important, is that eternal inflation isn't a special addition to the theory. It isn't an extra assumption you bolt on. It's what you get when you work the original equations carefully and honestly and include the quantum behavior of the inflaton field. It was, in a very precise sense, already there, hidden in the math. Waiting, Guth himself, looking back at his own theory with the full weight of these later developments, would write that inflation is, in his phrase, almost always eternal. Not sometimes, not in some models, almost always. For almost any inflating universe described by almost any reasonable inflaton field, if you follow the quantum mechanics carefully, eternal inflation is not an exotic possibility, it's the expected behavior. And this is where the phrase "the truth the inventors didn't want" stops being rhetorical and becomes, quietly, literally true. Because nobody asked for this. Nobody sat down and said, "Let's build a theory in which the universe is just one of infinitely many, each one a separate bubble in an eternally inflating sea." That would have been a very peculiar thing to set out to do. What Guth and Linde and Vilenkin were doing was trying to understand why our universe looks the way it does, why it's flat, why it's smooth, why the CMB temperature matches across the sky. The multiverse wasn't the goal. The multiverse was the uninvited conclusion that arrived when they did the mathematics honestly. And it wasn't comfortable. Guth's original 1980 version, the first inflation, had actually failed, quietly but definitively, for a reason connected to this very issue. In his original model, inflation ended not by the inflaton rolling smoothly down to its minimum, but by bubbles of true vacuum nucleating suddenly within the false vacuum, like ice crystals forming in supercooled water. The problem was those bubbles. They formed, but they were carried apart by inflation so violently that they could never coalesce, they never collided, they never merged into a smooth, reheated universe. Instead, they produced a cosmos that was almost entirely still inflating false vacuum, with tiny frozen bubbles scattered through it, too separated to combine. It was, in the technical language, a graceful exit problem. Inflation couldn't exit gracefully. It got stuck. The fix, Linde's fix, and independently the fix found by Albrecht and Steinhardt in 1982, was to change the shape of the inflaton's potential. Instead of a sudden jump from false vacuum to true vacuum, make the transition slow and smooth. Make the marble roll gently down a long, shallow slope rather than jumping off a cliff. This slow roll inflation heated the universe smoothly and produced the flat, uniform cosmos that matches our observations. It worked. It solved the graceful exit problem. But solving it required making the inflaton linger on that high plateau, rolling slowly for a long time. And lingering in the quantum world means quantum kicks have time to act. Lingering means that some fraction of the field gets kicked back uphill while the rest rolls down. Lingering, in other words, is exactly what enables the self-reproduction. The fix that saved inflation is the fix that made eternal inflation nearly unavoidable. The solution to one problem brought the multiverse in through the back door, and nobody could get it out again. They tried. The equations just kept giving it back. There's something almost poignant in that, I think. These were people trying to understand one universe, our universe, and doing it so carefully, so honestly, following the math with such discipline that the math handed them infinitely many. They didn't ask for the answer they got. But there it was. So, let's stay with what that actually means. What eternal inflation, taken seriously, actually implies. And it implies something that sits quietly at the edge of comprehension, if you try to picture it. While inflation is still going, in the vast, still expanding sea that surrounds what we'd call our corner of reality, pockets are falling out, here and there, like bubbles rising through carbonated water and popping at the surface. Each pocket is a region where the inflaton has finally rolled to its minimum, reheated, and settled into a hot fireball. Each one then expands and cools and forms structure over billions of years in whatever way its physics allows. Each pocket is its own universe. Our pocket, our bubble, is one of them. The entire observable universe, all 93 billion light-years of it. Every galaxy and filament and void, every photon that has ever reached a telescope, all of it is the interior of one bubble, one pocket that fell out of the inflating sea at some point in a deep and vanished past. But let's hold that thought for now, just rest it there. Because what happens inside those other bubbles, and how many of them there are, that's a story for the next few moments. And we'll get there slowly. For now, just let the image settle, a sea that never stops expanding. Scattered through it, quiet little islands of cooled, reheated space, each one vast beyond comprehension to anyone inside it. Each one with its own history, its own stars, its own billions of years of physics playing out, and ours with its flat geometry, its spectral tilt of 0.965, its hydrogen and helium and carbon and oxygen, its mountains and oceans and sleeping people, just one island among an endless tide of others, still forming, still budding off, moment by moment, into the dark. Let that be soft and slow for you. There's nothing alarming in it just yet. It's just enormously, quietly large. Take a breath, long and even. The picture is a strange one, but the physics that built it is the same physics that built the world you know. The same inflaton field that heated our universe into being, that rolled down, reheated, and gave rise to hydrogen, to stars, to carbon, is still doing its work out there, somewhere, beyond any horizon we can reach or see. Still rolling, still kicking, still making worlds. And the quantum jitters that seeded our galaxies, those same random fluctuations in a field smaller than thought, are doing the same thing in those still inflating regions. Seeding new overdensities, stretching to cosmic size, giving birth to structure in bubbles that may never know we exist, in a sea that may never end. The mechanism that built you is the mechanism that multiplies worlds. That's not a metaphor. That's what the equations say. And in a little while, when we've rested here, in this strange image, for just a moment, we'll ask the next question. The one that follows naturally. The one that makes this genuinely strange rather than just large. If those other bubbles exist, what are they actually like? Not just other universes, probably similar to ours. That's the hand wave. That's what you get in the videos that don't follow the physics all the way. Because when you do follow it all the way, when you take seriously not just the inflaton field, but the entire framework of modern physics in which inflation is embedded, you find that the answer is much stranger than probably similar. The answer might be, we have almost no idea. Because the laws of physics themselves, the ones we treat as fundamental, as fixed, as the bedrock of reality, may not be fixed at all. They may be local. They may be different in every bubble. And somewhere, right now, in one of those others, there may be a universe where the constants sit in values so different from ours that atoms themselves don't form. Where there are no stars, no chemistry, no structure of any kind, just a thin, cold fog expanding forever through empty space. And somewhere else, infinitely many somewhere else's, the constants may sit so close to ours that the physics is identical. Which means, if you follow the logic carefully and honestly, and flag it honestly as what it is, but that thread is for the next stretch of this quiet walk. Don't reach for it yet. Let it wait. There's no hurry here. The sea is still expanding. The bubbles are still forming. And we are, all of us, resting in one, warm and still and barely aware of the strangeness we're floating in. So here is the part of the story that the physics didn't plan for. Sit with that for a moment, if you like. There's no rush. You might already be close to the edge of sleep, which is perfectly fine. Let the words wash past. Let the ideas be half-formed, the way ideas are at this hour. The physics will still be here in the morning. And wherever you are right now, whatever lamp is still glowing, whatever blanket is pulled up, you're settled in exactly the right place to hear this next piece. Because this is the part that even the people who built the theory didn't want to find. This is the part that came anyway. We have to go back. Back to 1980. Back to Alan Guth, sitting with his equations at Stanford, realizing for the first time that you could explain the three biggest mysteries of the Big Bang in a single stroke. The horizon problem, the flatness problem, the monopole problem, all three dissolved at once the moment you allowed for that brief, explosive period of exponential expansion. Inflation was elegant, it was almost too clean, and Guth knew he had something real. But there was a catch. There is almost always a catch. In Guth's original 1980 version of the theory, inflation ended in a particular way. As the inflaton field rolled toward the bottom of its potential, think of it again as a ball rolling downhill. It didn't simply slide. In Guth's model, the field had to tunnel through a kind of barrier. The way a quantum particle can sometimes pass through a wall, it doesn't classically have enough energy to cross. And when it did, it would nucleate bubbles. Little pockets of true vacuum, of lower energy, surrounded by the still inflating false vacuum background. Those bubbles would expand, and eventually, so the thinking went, they would collide with each other, merge, and heat up into the hot particle soup that becomes the universe we know. It was a beautiful picture. In principle. In practice, it didn't work. The problem was the geometry. The inflating background between the bubbles was expanding so fast, exponentially, remember, doubling and doubling and doubling, that the bubbles could never actually catch each other. They nucleated. Yes, they grew. But the space between them stretched faster than the bubbles themselves moved outward. So the collisions that were supposed to reheat the universe and make ordinary matter never happened. The bubbles sat in an expanding sea and never found each other. Physicists call this the graceful exit problem, and in Guth's original model there was no graceful exit. The universe, according to those first equations, would be a cold, lumpy void of isolated, never-merging bubbles, which is not, as you might have noticed, what we see when we look at the sky. So the theory was broken. It was beautiful, and it solved three profound mysteries, and it was broken. This is the part of science that doesn't always make it into the popular telling. The initial breakthrough, the moment of inspiration, that gets remembered. The years of subsequent repair work, the quiet realization that the first draft doesn't quite function, that part is harder to frame as a triumph. But it's just as real and just as important, because it's in the repair work that the uninvited passenger arrived. In 1982, two separate groups of physicists, working independently, found a fix. Andrei Linde at the Lebedev Physical Institute in Moscow, and separately Andreas Albrecht and Paul Steinhardt at the University of Pennsylvania, both arrived at what became known as new inflation, or slow-roll inflation. The key change was in the shape of the inflaton's potential. That landscape of hills and valleys that determines how the field moves. Instead of tunneling through a steep barrier, the field in the new picture simply rolled slowly down a very gently sloping hill. Slowly enough that it took a long time to reach the bottom. Slowly enough that, in the meantime, space expanded by all the e-folds required. And when the field finally reached the bottom, it didn't produce isolated bubbles. It converted its energy smoothly and thoroughly into a hot bath of particles. Reheating, the Big Bang's thermal beginning. The graceful exit problem was solved. Inflation worked. And it made predictions that could be tested, and over the following decades, they were. So that's the good news. The theory was repaired, and the repair was good, and the universe it described was real. Here is the part that nobody quite planned for. When you take the new, repaired, slow-roll version of inflation and you look at it carefully, when you don't just treat the inflaton field as a smooth classical object rolling steadily downhill, but when you include the fact that it is a quantum field, and that quantum fields are never perfectly smooth, They are always flickering with tiny random fluctuations. You find something uncomfortable. Those quantum fluctuations don't all push in the same direction. In any given region of space, the field is rolling downhill on average. Yes, but quantum mechanics means there's always some probability of a kick uphill. A random jitter that pushes the field slightly back up the slope, back toward higher energy, back toward more inflation rather than less. In most places, most of the time, the downhill roll wins. Inflation ends. Reheating happens. A bubble of hot matter and energy forms. But not everywhere. In some regions, by pure quantum chance, the uphill kick wins. The field doesn't roll down. It stays high. Inflation continues, and here is where it gets strange, in the very specific way that the physics of exponential growth makes things strange. In an inflating region, space is doubling, and doubling, and doubling again. So a region that keeps inflating doesn't just persist, it grows. It grows exponentially. And the regions where inflation has ended don't grow at all, not in the inflationary sense. They've stopped. They're fixed in their size, these pockets of reheated matter, while the inflating background around them keeps expanding without limit. What this means is that even if only a tiny fraction of any given inflating region receives an uphill kick and keeps going, the total volume of inflating space keeps increasing. The region that's still inflating is always growing faster than the region that's stopped. So in terms of sheer spatial volume, the inflationary sea never shrinks. It perpetually generates new inflating territory faster than it loses old territory to reheating. Inflation, once started, can never fully stop. Not everywhere. It ends in places, in the pockets and bubbles that drop out. But the background, the eternal expanding sea of high-energy inflating space, that never goes away. It keeps producing new bubbles forever into the future, inexhaustibly, the way a fire keeps producing sparks as long as there's fuel, except in this case the fuel is the structure of the quantum vacuum itself, and the supply doesn't run out. Alexander Vilenkin was the first to describe this in 1983, and Andrei Linde developed the full picture through 1986 in what he called the chaotic, self-reproducing inflationary universe. The name is precise, self-reproducing. The inflating cosmos creates copies of the conditions for more inflation, endlessly, never arriving at a final state where everything has wound down. And Guth himself eventually came to the same conclusion. He has written and spoken about the fact that inflation is almost always eternal, that for the wide class of models that work, that fit the data, eternal self-reproduction is not an exotic add-on. It's the default. It comes with the territory. The multiverse, in other words, was not proposed as an exciting speculation. It wasn't invented to make the theory more dramatic or to solve some other problem. It fell out of the repair work. It was the uninvited passenger that climbed into the theory when Linde and Albrecht and Steinhardt patched Guth's graceful exit problem. Fix the one flaw in the otherwise beautiful picture, take quantum fluctuations seriously, and you find that the universe is not a single event, it's a process. An ongoing, never-ending process of budding and spawning and expanding, endlessly generating new pockets of space and matter and time. The inventors tried in various ways to get rid of it, or at least to wish it weren't there. But the equations are the equations. You can choose not to follow them into uncomfortable territory, but you can't make them say something different. So, let's follow them. If inflation is eternal, if the inflating sea keeps going forever, constantly nucleating new bubble universes, then what we call our universe, our observable cosmos, the whole 93 billion light-years of it. The thousands of billions of galaxies, every star that has ever burned, and every planet that has ever turned, all of it is the inside of one such bubble. One pocket. One tiny region where, at some particular moment in the deep past, the inflaton field rolled down and reheated and produced the hot dense beginning that became everything we see. 93 billion light-years. It sounds enormous. And by human standards, or even stellar standards, it is. But as a fraction of the whole, as a portion of the eternal inflating structure within which our bubble sits, it is essentially nothing. Less than nothing. There's a comparison that makes this vivid, or tries to, though it ultimately fails because the numbers are too large for any comparison to hold. Our entire observable universe is to the whole inflating multiverse as a single atom is to our observable universe. And even that understates it, because the multiverse is not just larger, but infinite, still growing faster the longer you wait. Our home. Everything we have ever mapped, every civilization that has ever risen and fallen, every thought that has ever been thought, inside one pocket, one among endlessly many. Now here is where the question you are probably half thinking becomes important. If there are all these other bubbles, what are they actually like? And this is where the physics takes a turn that requires a bit of care. Because the answer depends on something that goes beyond inflation itself. It depends on the structure of the theory that sits beneath inflation, the framework within which the inflaton field lives, and that framework has its own strange and still contested architecture. The framework is string theory. Or more precisely, what string theory implies about the space of possible physical laws. String theory is, very roughly, an attempt to unify all the forces and particles of nature within a single mathematical framework by positing that the fundamental constituents of reality are not point particles but tiny, vibrating one-dimensional strings of energy. Different vibration modes correspond to different particles. The mathematics is extraordinarily rich and extraordinarily difficult. And one of its features, a feature that turns out to be enormously important for the question of what neighboring bubbles might be like, is that the theory admits not one solution, but an astronomically large number of them. Each solution corresponds to a different configuration of the extra dimensions that string theory requires, dimensions curled up at scales far too small to see. Like tiny rolled-up tubes that we have no direct access to. And each different way of curling and folding those extra dimensions gives rise to different effective physics in the 4 large dimensions we do inhabit. Different particle masses, different force strengths, different values for the constants, the number of distinct solutions, distinct possible configurations, distinct possible sets of physical laws that string theory permits is estimated to be something in the neighborhood of 10 to the power of 500. Let me say that again, slowly, because the number is important. 10 to the 500th power. Written out, it would be a 1 followed by 500 zeros. A page full of zeros, more than a page. For comparison, the total number of atoms in the entire observable universe is only around 10 to the 80. The number of possible vacuum states in the string landscape is incomprehensibly, grotesquely larger than the number of atoms in everything we can see. The physicist Leonard Susskind gave this collection of possible states a name. He called it the cosmic landscape, which is also the title of a book he wrote in 2005, laying out the argument. The work that formalized the structure of the landscape was done by Raphael Bousso and Joseph Polchinski, who showed in detail how the different configurations could be stabilized. and how each configuration would correspond to a different value of the cosmological constant, the energy density of empty space, as well as other physical quantities. What does this have to do with eternal inflation? Everything. If the inflating sea is eternal, and if bubbles are constantly nucleating within it, then each bubble that forms doesn't have to settle into the same vacuum as every other. Just as Guth's original model had the field tunneling from a false vacuum to a true one, the bubbles in the eternal inflationary picture can in principle tunnel into any of the available vacua, any of the possible solutions on the landscape. And if there are roughly 10 to the 500 of those, then different bubbles may settle into different ones, may develop after reheating with a completely different set of fundamental constants than ours, a different strength of the electromagnetic force, a different mass for the electron, a different value of the cosmological constant, the energy density that drives space to expand. And some of those combinations, most of them by some reckonings, won't permit anything like the physics we know. The electromagnetic force might be so strong that atoms blow apart before they form, or so weak that electrons don't bind to nuclei. The cosmological constant might be so large that space tears itself apart before gravity has a chance to pull matter into clumps, or so negative that the bubble collapses back on itself in a cosmic crunch before a single star ignites. In those bubbles, there are no atoms, no chemistry, no stars, no heat, no long, slow processes of complexity. Just whatever sparse quantum fields exist in that vacuum, dispersing into a void too hostile for structure of any kind. Physicists sometimes describe the physical constants we live with, the values of the fine structure constant, the masses of quarks, the cosmological constant itself, as finely tuned, which is a technical way of saying if you adjusted them even slightly, the world would be unrecognizable or non-existent. Our constants sit in a narrow window that permits atoms, chemistry, stars, planets, and, eventually, people lying in the dark thinking about physics. That fine-tuning has always been somewhat uncomfortable. It suggests either extraordinary luck or a deeper explanation we haven't found, or something else entirely. And the something else that the multiverse offers is this: if 10 to the 500 types of bubbles exist, drawn from all available vacua, then some of them, just by sheer combinatorial chance, will have constants in the narrow life-permitting range. And since life only arises in those bubbles, those are the only ones where anyone can ask the question of why the constants are what they are. There's no one in the bubbles with wrong constants to wonder about it. This argument that we find ourselves in a life-permitting universe because only life-permitting universes contain life to be found goes by the name the anthropic principle. It is not universally loved. It feels, to many physicists, like explaining away a question rather than answering it. But it has at least one concrete, verifiable success to its name, which we'll come to a little later in our walk. For now, the point is this: the laws of physics as we know them, the constants, the masses, the force strengths, all the quantities that textbooks list as fundamental, may not be fundamental in the way we thought. They may be local. They may be the particular values that the inflaton settled into when our bubble nucleated. In another bubble, the laws are different, equally real to whoever or whatever might exist there, but different. As Susskind and others have put it, the laws of physics might be local bylaws, not statutes of the universe, but the zoning codes of our particular neighborhood in an incomprehensibly vast city where every district runs by its own rules. That is a strange thought to carry into sleep. But let it settle gently. You don't have to resolve it tonight. Nobody has. And now for the number. The honest number. The one the title promised you. How many universes does eternal inflation predict? Not millions, not billions, not trillions of trillions, not any finite number, however large. Infinite, the self-reproducing inflationary sea never stops. Into the future it goes on forever. This is established by the mathematics for the class of models that work. It keeps spawning new bubbles, without end, without a final count. And each of those bubbles may draw from the cosmic landscape of 10 to the 500 possible vacuum configurations. So the answer, if we take the theory seriously, is infinitely many bubbles, each potentially from an astronomically large menu of possible physical laws. Infinity is not a number you can picture. This is a known limitation of human cognition, not a failure on your part. We evolved to count berries and estimate distances, not to hold infinity comfortably in mind. But there is one consequence of infinity that is worth sitting with, because it is the most genuinely strange thing that this whole thread of physics leads to, and because Andrei Linde himself has spoken about it. If the number of bubble universes is truly infinite, and if each one is governed by constants drawn from a finite menu, even a menu as large as 10 to the 500, then every possible configuration must occur infinitely many times. Every combination of constants that the landscape permits, by the sheer pitiless logic of infinite repetition, appears not once, but endlessly. Which means, and this is where the logic gets quietly vertiginous, and where you should hold the conclusion at arm's length as the T2 extrapolation that it is, a consequence of the framework rather than an established fact, offered honestly as Linde's own statement of what the theory implies, which means that among those infinite bubbles, there will be infinitely many where the constants are identical to ours, where the physics is the same, where the same processes of star formation and planetary chemistry and biological evolution unfold, where, given enough time and enough space inside each of those bubbles, and there is enough, because the inside of each bubble is enormous, the same or similar configurations of matter arise. Again and again, infinitely many times. Somewhere, Linde has said, in the landscape of eternal inflation, there are infinitely many copies of our observable universe, infinitely many galaxies like ours, infinitely many planets like this one. And if that is so, then somewhere, not as a metaphor, but as a straightforward consequence of infinity and finite types, there is a version of this night, a version of you, lying in the same kind of dark, listening to the same kind of voice, thinking about the same strange ideas, not because they chose to be, or because something planned it, but because infinity doesn't permit exceptions. Everything that can happen in the space of possible physical histories happens infinitely often. That is, if the framework is right, and it might not be. It is an extrapolation from tested inflation into untested eternal inflation into the full-string landscape, a chain of steps each one of which is less certain than the last. You should not take it as settled. None of the physicists involved do. But it is what the mathematics suggests, and the mathematics comes from the same theory that correctly predicted the temperature variations in the cosmic microwave background and the flatness of the universe and the spectral tilt that the Planck satellite measured. The chain that leads from those confirmed predictions to the infinite self-replicating multiverse is long, but it is not invented. It is a logical extension of the same framework. Where it leads is simply unusual. Linde's version of the statement has a particular quality to it. He speaks about it not with triumphalism, but with a kind of careful wonder, the wonder of someone who spent decades working out equations that led somewhere he didn't fully expect. He found that if the chaotic self-reproducing picture is right, then the universe as a whole is more like a living thing than a static object, constantly generating new regions, each one a complete world, each one subject to its own configuration of the deepest laws of nature. An endless generative process, indifferent to any particular outcome, producing everything possible because it has infinite time and infinite volume in which to do so. That image of the cosmos as an eternally self-generating structure, bubbling and branching without end, is, in a very specific sense, the answer to the title's question. This is how many universes the best theory of the Big Bang predicts. Not a large number. Not a number at all. A process that never finishes counting, which might feel right now, at this hour, like a thing that should be frightening. The title said so. Terrifying, and there is something in it that deserves that word, not as hype, but as honest recognition of what the vertigo actually is. The vertigo of learning that what you thought was the universe, the whole, the totality, the container of everything, is a single small pocket in a structure so large that it cannot, in principle, be fully comprehended. That the laws you live by may be local ordinances, that somewhere, by the cold arithmetic of infinity, this moment is repeated. There is something that deserves the word terrifying in that yes. But there is also, if you let it settle a little longer, something else. Because the same inflaton field that produced this endless sea of worlds also produced you. Specifically, personally, the quantum fluctuations that made inflation eternal, that made the inflating sea keep going rather than stop, are the same quantum fluctuations that in our bubble were stretched to cosmic scale and became the seed over-densities that gravity grew into galaxies and stars and planets and everything that lives on them. The mechanism that multiplies worlds is the same mechanism that built this one. The wildness that generates infinite variety is the same wildness that generated you. And that is not a small thing to take to sleep with you. But it does raise a question, a very practical and very honest question, the kind of question that distinguishes this from a fairy tale. If all these other bubble universes exist, is there any way to reach one? Any way to see one? Any way to know they're there at all? And here is where the physics becomes, in a particular way, almost brutal in its honesty. Because the answer, and we'll take it slowly, there's time, is almost certainly no. And the reason is not that we lack the technology. It is not an engineering problem that a sufficiently advanced civilization might solve. It is, as far as we can tell, a fundamental feature of the geometry of space itself, built into the structure of what eternal inflation means. The space between our bubble and any other bubble is not empty space, the ordinary kind you could in principle cross if you had enough time and a fast enough ship. It is inflating space. It is still in the grip of the repulsive physics that drove inflation in the first place, still doubling and doubling and doubling. And what that means for any hypothetical journey is this: the moment you leave our bubble and enter the inflating background, which is already a thing that cannot actually be done, but follow the thought, the gap between you and any other bubble would be growing faster than you could cross it. Faster than light can cross it. You could travel at the speed of light, which is already the fastest anything can move, and the distance to the nearest neighbouring bubble would be increasing faster than you approached it. Not slower. Faster. The gap opens faster than it closes, no matter how fast you go. This is not so different, in its basic logic, from something we already know about our own universe. There is a boundary around us called the cosmic event horizon, the distance beyond which space is expanding faster than light can travel across it. Galaxies beyond that boundary are right now receding from us faster than light. We can never reach them. We can already see light from many of them, because that light was emitted when they were closer and the expansion hadn't fully carried them away. But no signal we send today will ever catch those galaxies, and no signal they send today will ever reach us. They are causally disconnected from us. Forever, the inflating space between bubble universes makes that kind of separation look mild. The cosmic event horizon in our universe is a consequence of dark energy, the mild present-day repulsion that makes up roughly 68% of the cosmos's energy budget. The inflating background between bubbles is driven by the inflaton's false vacuum energy, which is many orders of magnitude more powerful than dark energy. The expansion between bubbles is not gently accelerating. It is exponential, violent from the perspective of anyone trying to cross it. So the other bubbles are not just far away, they are receding from us at rates that make the concept of far away almost meaningless. There is no path between us and them. There is no road, because the road is being unrolled faster than any traveller can walk it. Forever. That is the honest answer to why can't we reach one. Not it would take too long. But the concept of getting there is geometrically impossible, because the space between here and there is always growing faster than anything can move. And seeing them? That is its own story, and there is one slim chance, one narrow window, searched for carefully and methodically, and yielding a result that is honest and important. But that belongs to the next part of our walk. And you are perhaps already drifting, which is exactly right. The ideas don't have to be held tightly. They can float. They can dissolve into the warm, comfortable nothing of sleep, while some quieter part of you keeps the thread. The sea is still expanding. It has never stopped. Somewhere in it, infinitely far, unreachably far, in a direction that isn't quite a direction, because directions only make sense inside a bubble. Another world is cooling down after its own reheating, or has already been cold for billions of years, or is not yet capable of being cold because atoms don't form in its physics, because the laws there are not our laws, because the inflaton rolled down a different slope and settled into a different place on the landscape, and everything that followed was different, unrecognizably different, all the way down. And here, inside our bubble, you are warm. The blanket is the right weight. The dark outside the window is the ordinary kind. The atoms in your hands, the electrons, orbiting their nuclei at distances determined by the exact, particular, life-permitting value of the electromagnetic force in this bubble, are doing what they have always done, quietly obeying the local bylaws, keeping you together. That is not nothing. That is, by some reckonings, the most improbable thing in the infinite catalogue of what could have been. So, let's talk about getting there. You might wonder, if all these bubbles are real, if other universes are out there right now, cooling down or still reheating, filled with their own strange constants and their own local physics, couldn't we someday go? Couldn't some future civilization, impossibly advanced, point a ship in the right direction and simply travel? The honest answer is no. And the reason is not a matter of technology. It's a matter of geometry, and of what the space between bubbles is actually doing. Remember what we said about the inflating sea, the background that never stopped, the eternal froth of space that keeps expanding while pocket universes like ours settle out of it. That sea is not sitting still. It is expanding exponentially right now, at this moment, in the same violent, runaway fashion that drove our own first instant. The space between our bubble and any neighbouring bubble is not a fixed distance. It is a growing one. A relentlessly, unstoppably growing one. Here is what that means in practice. Imagine you set off at the speed of light, the absolute cosmic speed limit, the fastest anything in the universe can travel. You'd think that eventually, given enough time, you'd close the gap to another bubble. But you can't. Because the space between you and that other bubble is itself expanding faster than you're crossing it. Every second you travel, the destination moves farther away than your movement has brought you closer. You are not running toward a fixed wall, you are running toward a wall that is retreating faster than you can run. This is not so different, actually, from something happening right here in our own universe. You may have heard the phrase observable universe, the 93 billion light-year sphere of space we can actually see. Beyond that boundary, galaxies exist. But the universe is expanding, and at great enough distances, that expansion carries things away faster than light can travel. Those far galaxies are moving away from us faster than their own light can reach us. They are beyond what's called the cosmic event horizon, permanently beyond it. Not because they're hidden by anything solid, but because the space between us is stretching too fast. We'll never see their light. They'll never see ours. Now take that idea and make it vastly more extreme. The inflating sea between bubble universes isn't expanding at the gentle rate our dark energy-driven universe expands at today. It's expanding at an inflationary rate, the same exponential violence that stretched a region smaller than a proton to the size of a cosmos in a fraction of a second. The distance to another bubble is not just growing. It's growing at a rate that makes our own cosmic event horizon look like a quiet afternoon stroll. No ship, no signal, no beam of light. Nothing crosses that gap because the gap is always opening faster. And there's something even stranger buried in this. The inflation between bubbles means the bubbles themselves are being carried apart. Even if two bubbles formed close together, even if they were neighbours in the landscape freshly hatched, the inflating space between them would sweep them away from each other before they could grow large enough to overlap in any meaningful sense. The sea doesn't just separate them, it preserves the separation forever. So no, you can't get there. And you never will. Not because the universe is unkind, but because that is simply what the geometry does. Inflating space is not a road, it is a current moving faster than any ship. But here's where the story takes an interesting turn. Maybe we don't need to go there. Maybe there's a way the other universe comes to us, or, more precisely, came to us a very long time ago, and left a mark we might still be able to read. Think about what happens when bubbles form in the inflating sea. They don't all form at the same moment, in the same place, far apart and safely isolated. Some of them, early on, form close enough together, close enough that before the space between them has expanded too far, the edges of two young bubbles could collide. Not a gentle meeting, a collision. Two expanding regions of reheated, cooling space pressing against each other along a boundary, like two soap bubbles touching on the surface of water. Each one pushing into the other's territory before the gap between them could grow. If that happened to our bubble, if, in the very early moments after our reheating, our universe collided with a neighbouring bubble, the collision would leave a mark, a specific kind of mark, a circular pattern on the oldest light in our sky. That oldest light is the cosmic microwave background, the CMB, the faint afterglow of the hot Big Bang, a nearly perfect bath of microwave radiation that fills the universe from every direction. We've been studying it for decades. It is the richest map of early cosmic history we have. And if a bubble collision happened, the physics of how it would interact with that map is actually calculable. It wouldn't be random or diffuse. It would be a disk. A circular region, probably slightly warmer or cooler than its surroundings, with a distinct edge, a bruise essentially, left by the impact of another universe pressing against ours. Physicists looked for exactly this, not in a casual, hopeful way, in a methodical, systematic, careful way. Stephen Feeney, Matthew Johnson, Hiranya Paris, and their collaborators went through the data from the MAP satellite, one of the most precise maps of the cosmic microwave background assembled at the time, and later from the Planck satellite, which was more precise still. They searched for the specific circular anomalies that a bubble collision would produce. They built statistical tools designed to distinguish a real collision signal from the ordinary noise and variation that exists in any map of the microwave sky. This was around 2011 and the years that followed. Real searches, real data, real methodology. And the result was nothing confirmed. There were some statistical hints, a handful of anomalous features that Feeney and Johnson's team noted cautiously, but nothing that rose above the threshold of significance. Nothing that held up as a definitive detection. The CMB, as best we can read it, shows no unambiguous bruise from a colliding universe. There are two ways to read that result. One reading is, maybe there are no other bubbles, and eternal inflation is wrong. The other reading, the one most physicists in this field would offer, is that a bubble collision might never have happened close enough to us to be detectable, or happened in a direction we can't read clearly, or left a signal too faint for even Planck's extraordinary sensitivity to catch. The absence of a confirmed detection doesn't rule out the multiverse. It rules out one particular scenario in which an early collision was close and strong and geometrically favorable. But here is the thing worth sitting with, quietly, for a moment. The only fingerprint eternal inflation's multiverse could plausibly leave. The one testable trace, the one thing we might actually see, has been looked for, carefully, and it hasn't been found. We looked. The sky gave us back ordinary noise, ordinary variation, the ordinary beautiful complexity of the microwave background. No bruise, no ring, no mark from a neighboring world. That is not a failure of science. That is science working exactly as it should. Honest, methodical, open about what it found and what it didn't. And it is the thing that makes the next part of our walk so important. Because now we have to ask the hard question, the one that has been sitting at the edge of this whole conversation, patient and unavoidable. If we can't reach another bubble, if the inflating space outruns any ship or signal, and if the one measurable fingerprint a collision might leave hasn't been found, then what exactly is the status of all this? Is the theory of the multiverse, of eternal inflation, and infinitely many bubble universes actually science? Or has it drifted into something else, something beautiful and mathematically coherent and philosophically fascinating, but no longer quite the kind of claim that science, in its traditional sense, can test or falsify? This is not a question with an easy answer, and the people arguing about it are not fringe figures, they are the architects of the theory itself. Let's start with the sharpest version of the challenge. There is a philosopher named Karl Popper. He died in 1994, but his ideas are very much alive, who argued that the defining feature of a scientific claim is falsifiability. A claim is scientific, in Popper's framework, if there exists some possible observation or experiment that could, in principle, prove it wrong. Not that we have to actually perform the experiment, just that we can conceive of what being wrong would look like. If a theory makes no prediction that could ever be contradicted by data, then it is not science in the traditional sense. It may be philosophy or mathematics or metaphysics, but it is not the kind of thing we can test. Now apply that to eternal inflation. The complaint, made forcefully and for years by Paul Steinhardt, one of the very physicists who helped develop inflation in 1982 alongside Andreas Albrecht, is that eternal inflation predicts essentially everything. Because there are infinitely many bubble universes, and because they can have any of the roughly 10 to the 500 possible sets of physical laws that the string landscape offers, literally any observation you could make in any universe is predicted somewhere. And if a theory predicts everything, it effectively predicts nothing. Nothing that could distinguish it from a theory making the opposite prediction. Steinhardt has argued this openly, in papers and lectures, with the particular force of someone who built the thing he's criticizing. A man who helped construct the house now says the house doesn't meet the standards he would want a scientific theory to meet. And he's not alone. In 2014, two distinguished physicists, George Ellis, a cosmologist who had collaborated with Stephen Hawking, and Joe Silk, an astrophysicist at Johns Hopkins, wrote an essay in the journal Nature. It was titled Scientific Method: Defend the Integrity of Physics. Their argument was pointed and deliberate. Theories that are genuinely untestable. Theories that have retreated permanently beyond the reach of any experiment should not be accepted on the grounds of mathematical elegance or philosophical appeal alone. Allowing that, Ellis and Silk warned, betrays the tradition of science, the tradition that says we keep our grip on the physical world through evidence, through the willingness to be proven wrong. It is a serious charge, coming from serious people, and it deserves to be heard on its own terms before we hear the reply. The reply comes from other serious people. Alan Guth, the man who started all of this in 1980, whose original model was imperfect, and whose name is on the theory's birth certificate, has been willing to defend the broader framework. So has Andrei Linde, and so, perhaps most carefully in recent years, has Sean Carroll, a theoretical physicist who has thought hard about exactly where the boundaries of science lie and whether Popper's criterion is quite the right instrument for the job. Carroll's argument, laid out in a 2018 essay called Beyond Falsifiability, is roughly this: Popper's falsifiability standard is a useful rule of thumb. But it's too blunt an instrument for modern physics. Science has never run purely on falsifiability, it has also run on what philosophers call abductive reasoning, or inference to the best explanation. We accept a theory when it best explains the evidence we have, when it is coherent, when it is the most parsimonious account of a wide range of observations. By that standard, inflation, the tested, data-confirmed part of it, the part that explains the flatness and the horizon and the spectral tilt the Planck satellite measured, is as well supported as any theory in physics. The multiverse extension follows mathematically from the same framework. We should hold it provisionally, with appropriate uncertainty, as the best current account of what the equations imply. But throwing it out just because the far reaches of its implications are beyond our telescopes may be throwing out the physics along with the speculation. Guth himself has pointed out that inflation's core is not in question. The Planck satellite confirmed the spectral tilt, that small but measurable deviation from perfect scale invariance. N underscores sitting at approximately 0.965 rather than exactly 1, precisely what simple inflation predicts. The flatness is confirmed, the horizon problem is solved. The theory makes quantitative predictions, and they come out right. The multiverse is what happens when you take that tested core seriously and let the quantum mechanics of the inflaton field do what it naturally does. To throw out the multiverse, you'd have to throw out either the quantum mechanics or the field theory, and neither of those is on offer. So the argument has a shape. On one side, the multiverse is an unfalsifiable extrapolation, and science without falsifiability loses its anchor to reality. On the other side, the tested core is solid, and the multiverse is what the math implies. You can hold it as the best current framework while remaining genuinely open to revision. Neither side is being reckless. Neither side is obviously wrong. And the debate is, honestly and openly, unresolved. That unresolved tension is not a flaw in this story. It is the story. But there is one more layer here, hiding quietly beneath the falsifiability debate, and it is worth knowing about even if it makes your head swim a little, which is, at this hour, probably fine. Even if we accept that eternal inflation produces infinitely many bubbles, there is a deep mathematical problem at the center of that picture, a problem that even the theory's most committed defenders openly acknowledge. It is called the measure problem. Here is the difficulty. If there are infinitely many bubble universes, and you want to compute the probability of something, say the probability that an observer in a randomly selected bubble finds a universe with our particular value of the cosmological constant, you need to compare two infinite sets. How many bubbles have our cosmological constant versus how many have a different one? But comparing infinite sets is not straightforward. There is no single, obvious, natural way to do it. You have to choose what mathematicians call a measure, a rule for weighting the infinities against each other, and different reasonable choices of measure give wildly different answers. This is not a minor technical inconvenience, it is a foundational problem. Andrei Linde, Alexander Vilenkin, Raphael Bousso, Alan Guth, they have all worked on this, and they have not converged on a solution. Different proposed measures sometimes give results that are not just different from each other, but paradoxical, strange, troubling in ways that go right to the question of what it means for an observer to exist at all. One famous version of the problem involves what are called Boltzmann brains. The worry works like this. In a vast enough universe, or a vast enough collection of universes, extremely improbable things happen, simply because there is enough time and space for random thermal fluctuations to produce them. A Boltzmann brain is a hypothetical disembodied mind that pops into existence through pure random fluctuation, finds itself briefly aware, perhaps experiencing a false memory of being a person on a planet, lying in a warm bed, listening to a calm voice, and then dissolves back into equilibrium. In an eternal, infinite multiverse, some proposed measures suggest that Boltzmann brains should be vastly more common than genuine observers like us, actual biological beings in actual long-lived universes who arrived here through billions of years of physical and biological history. If that's true, then any observation you make is more likely to be the momentary hallucination of a Boltzmann brain than the coherent experience of a real person, which is, understandably, not a comfortable conclusion. And it suggests that something is wrong with the measure being used, that a good measure should predict that real observers like us are typical, not vanishingly rare accidents in a sea of brief, fluctuating minds. But finding such a measure has proven surprisingly difficult. Guth, Vilenkin, Busso, all of them have proposed candidates. None has been universally accepted. The measure problem is one of the genuine open frontiers of theoretical cosmology, and the physicists working on it say so plainly. That honesty is itself a kind of value. It means the people working on these questions have not lost their grip on the difference between what they know and what they are working toward. And now, and then we will rest, I promise, one final piece. If the multiverse is real, it offers something remarkable. An answer, or at least the beginning of an answer, to one of the oldest puzzles in physics. Why do the constants of nature have the values they do? Think about the numbers that define our universe: the strength of gravity, the mass of the electron, the value of the cosmological constant, the energy density of the vacuum, what we now call dark energy. These numbers sit in extraordinarily narrow ranges. If gravity were a little stronger, stars would burn out too fast for anything to evolve. If the cosmological constant were even slightly larger than it is, the universe would have expanded so fast after the Big Bang that galaxies could never condense. If the electromagnetic force were different, atoms wouldn't bind. The window in which life, in any form, can exist is absurdly narrow compared to the full range of values that are mathematically possible. And yet, here we are. This is the fine-tuning problem, and for a long time it sat there, uncomfortable and unexplained, a strange coincidence that seemed to demand either a designer or a deep reason that nobody had found. But if eternal inflation is real, if there are infinitely many bubble universes, each with different constants drawn from the string landscape's vast menu of possibilities, then the fine-tuning problem transforms. It doesn't dissolve, it relocates. The vast majority of possible universes produce nothing recognizable as life. Atoms don't form, or stars don't ignite, or the expansion tears everything apart before gravity can gather it. And we find ourselves in one of the rare life-permitting bubbles for the simple, undramatic reason that there is no one in the barren ones to notice. This is the anthropic principle. It can sound like a cheat, like explaining fine-tuning by saying, well, of course. Here we are. But in the hands of a careful physicist, it becomes something more rigorous. In 1987, more than a decade before the discovery of dark energy, a physicist named Steven Weinberg used anthropic reasoning to make a quantitative prediction. He asked, if the cosmological constant can take a wide range of values across bubble universes, and if observers only exist in universes where galaxies can form, then what range of values should we expect to measure in our universe? He did the calculation. He predicted that the cosmological constant should be small but non-zero, not zero, and not large, but sitting in the narrow window where structure can still form and something like life can exist. In 1998, Saul Perlmutter, Brian Schmidt, and Adam Reyes discovered, from observations of distant supernovae, that the expansion of the universe is accelerating. There is a dark energy, a non-zero cosmological constant, driving it apart. Its measured value sits very close to the range Weinberg had predicted a decade before, using only the reasoning that observers must be possible. This is not proof of the multiverse, it is not confirmation of eternal inflation, but it is a striking success, a prediction made before the data arrived, and a measurement that came in where the prediction said it should. That is the kind of thing scientists notice, and it gives the anthropic framework a quiet, stubborn kind of support that is hard to simply wave away. Now there is one last thread. People sometimes wonder if eternal inflation goes on forever into the future. If the sea of inflation keeps churning and bubbles keep forming without end, does that mean the universe has always existed? Is there no beginning? Did this process simply always be? The answer is no. And we know this with unusual confidence. In 2003, three physicists, Arvind Borde, Alan Guth, and Alexander Vilenkin, published a theorem. It is called the Borde-Guth-Vilenkin theorem, and what it says, in its essential form, is this: any universe that has been expanding on average throughout its history cannot have been expanding forever into the past. It must have had a beginning. The theorem is remarkably general. It doesn't depend on the specific inflaton model or on the details of what drove the expansion. Any eternally inflating space, if it has been expanding on average, must have started somewhere. So eternal inflation is, in a precise sense, a misnomer in one direction. Into the future, it never stops. Bubbles will always form, the sea will always expand. There is no last universe. But into the past, there is a boundary. A first moment. Vilenkin has proposed ideas about quantum creation from nothing, a universe tunneling into existence from a state with no classical time, the way a quantum particle can cross a barrier that classical physics says it cannot. But these are genuine speculations from genuine physicists, honestly labelled as such. What came before the beginning? Or whether before is even a meaningful word when time itself is just beginning? That remains, beautifully and honestly, open. What we can say is this: even if everything we have talked about tonight is right, even if inflation is real and eternal, and the sea goes on producing bubbles forever, and there are infinitely many universes with infinitely many law sets, even then, it all started somewhere. There was a first moment, something that was not, and then was. The endlessly expanding future does not rescue us from a beginning any more than an infinite ocean rescues a ship from the port it left. And so here is where we have arrived, on this long, slow walk through one of the strangest ideas in all of physics. We started tonight with a number. How many universes does the best theory of the Big Bang predict? And the answer, the honest, careful, physics-grounded answer, is this: if inflation is right, and if quantum mechanics does what it naturally does to the inflaton field, and if the string landscape is as rich as the mathematics suggests, then the number is not large. It is not very large. It is, in the most direct reading of the math, unbounded, infinite, not a metaphor for a great many. Literally without end. Literally growing at this moment. Literally never stopping. Our entire observable universe, every galaxy you have ever seen in any image, every star visible to the naked eye on the clearest night, the whole 93 billion light-year sphere of everything we can detect with every instrument we have ever built, is the inside of one pocket, one bubble, one of endlessly many, floating in a sea that has never stopped expanding. And the laws that govern our bubble, the mass of the electron, the strength that holds the nucleus together, the precise value of the cosmological constant that dark energy carries, those may be local to us. Local bylaws in one municipality of an infinite country, where each municipality settled into its own rules at the moment its inflaton field came to rest, drawn from a menu so vast the number of options has 500 zeros after it. And somewhere in that infinite catalogue, not as a metaphor, but as the honest logical consequence of what infinity means, there are bubbles where the constants fell almost exactly as ours did, where atoms form and stars ignite and planets cool and something like life begins. And somewhere among those, with the quantum choices running differently at each branch and each moment, something recognizable as you is going about something recognizable as a night. Not you. Never reachable by you, never visible to you, because the inflating sea between you and that place is opening faster than light, faster than anything, faster than any gap could ever be closed. But there, according to the math, that is the terrifying truth the title promised. And I hope, I sincerely hope, as I hope with all of these late-night walks, that it lands for you not as terror exactly, but as vertigo. The good kind. The kind that loosens something behind the ribs. The kind that makes the ceiling above your bed feel a little more interesting, a little more strangely inhabited by the fact of your being there and looking at it. Here is the thing I want to leave with you. Whether eternal inflation is right, whether any of the multiverse is real, whether it remains permanently in the beautiful but unconfirmed corner of physics, or whether someday some new tool or theorem gives us a firmer foothold, none of that changes what you are, right now. You are made of quantum fields. The same quantum fields that inflated and fluctuated and reheated into this universe, that rippled with tiny jitters in the first fraction of a second of time, that stretched into slight overdensities and thickened over billions of years into galaxies, and inside them stars, and inside those stars the forges that made heavier atoms and scattered them out into space where they gathered into new stars and planets, and eventually into whatever surface you are lying on at this hour. The fluctuations that may have seeded infinite worlds also seeded you. The inflaton field did not distinguish. It was indifferent and relentlessly fertile, and some very small and improbable fraction of what it produced turned out to be capable of lying still in the dark and wondering about the rest of it. And here you are. Lying still. Wondering, that is, by any reasonable accounting, extraordinary, by the laws of this bubble, the particular, locally determined, life-permitting constants of this one pocket among infinitely many, the matter in you has organized itself into something that can ask what the matter beyond it is doing. And even if the answer is forever out of reach, even if the inflating sea can never be crossed and the CMB carried no bruise to find, the asking itself is something the universe is doing through you. Right now. While you are perhaps already drifting. While the lamp is still on or the room is fully dark. While some part of you holds the thread and some part of you lets it go. I asked, near the beginning of tonight's walk, where you're listening from, what time it is in your corner of the world. I'll ask one more time now, here at the end, because I mean it, and because the answer is, in the broadest sense, one small data point in the infinite catalogue of where consciousness is quietly happening in this bubble tonight. That seems to me like exactly the kind of thing worth knowing. You don't have to answer, you don't have to remember any of this in the morning. The ideas will still be here when you wake, the sea will still be expanding, the bubbles will still be forming. The measure problem will still be unsolved, and Steinhardt and Guth will still be on opposite sides of a fascinating and unresolved argument. And Weinberg's 1987 prediction about the cosmological constant will still be sitting there, looking quietly and almost maddeningly prescient. None of it goes anywhere. And you have nowhere to be. If tonight helped you drift off to something wider, something calmer, something that made ordinary darkness feel a little less ordinary. A like and a subscribe means a great deal to a small channel like this one. Grandpa's Late Nights runs on the kindness of people who find something here worth staying for. And to those of you who have been here before, who have come back on other nights for other walks, thank you. Sincerely and quietly and without any fuss, thank you. Sleep well wherever you are. The laws of this bubble are doing what they always do, holding the electrons in their orbits, keeping the nuclei bound, running the slow warm chemistry through every cell of you. The observable universe is 93 billion light-years across. That is, by any measure, more than enough room for one good night's rest. Good night, kiddo. Grandpa'll leave the porch light on.